We're continuing with the pre-algebra chapter in the algebra textbook. In this video, we're going to go through the last section, section 6, which you can see is on rational expressions and more operations on radicals. Now, in regards to the more operations on radicals, as we've gone through these sections, there's been different parts where we do operations with radicals. We multiply single-term radical expressions, add radicals, multiply multiple-term radical expressions with distribution. So in one of the upcoming videos, we'll do an example problem video that includes examples with all of the operations on radicals that we've talked about in the last few sections. Okay, but the more main topic in this section is rational expressions. Okay, so as we talked about in the previous section, one of the things that we're going to be doing in algebra is putting expressions into different categories. And then once we learn equations, the equations will be put into categories, but the categories that equations are in are based on the expressions that are in the equations. So now we talked about in the previous video a certain type of expression that you label as a polynomial. Okay, now here we're going to talk about another category of expressions called a rational expression. Now it might seem like that there's so many different categories to remember that it's overwhelming, but it just seems overwhelming. It's not nearly as complicated as you would think. And the reason why I say it's not nearly as complicated as you would think is because remember, so the only types of variables that we've talked about so far in this course are x to a positive integer power, x to the 0, I guess you could put x to the 0 in this category, x to a negative integer power, and then x to a rational exponent power. Okay, now, but there's also radicals, but remember, radicals are fall into this category. Okay, and that's it. Now, yes, we do have addition, subtraction, multiplication, and division, but that's not like an operation on a variable. That's I could add these two. I could subtract these two, however I add, subtract, multiply, or divide, it doesn't change the type of expression I have. So the only thing that's putting an expression into a certain category, it's not about adding, subtracting, multiplying, or dividing. It's about the types of terms or expressions you have. And up to this point, there's only 3 different types. Now you might say, well, okay, that's fine, but once we get into the main chapters of algebra, there's probably going to be so much more. No, there's going to be 2 more. In the entire algebra, in all of algebra, there's going to be 2 more. And really, in actuality, those 2 more types of operations that we're going to learn are like offshoots of this. So like an exponential is going to be, that's a function. So we'll learn what a function is later, but you have some base, which is just a number, to the power x. And so in that case, x could be any number. So it could be an integer, it could be a positive or negative integer, a rational exponent. Oh, we also have to learn like what x to the pi is, or irrational exponent. But other than that, that's it. And so you can see an exponential is just packaging all of this into like an expression, because x can be, you have any number here, and x can be any number, right? Any number you can think about on the real number line, or we'll learn a complex number, but sticking to the real number line, x can be irrational, rational, or positive, negative integer. So it's all like packaged into this one function here. And then a logarithm is just like, it's the inverse of this. It's the opposite of this, in the same way that, so log base b of x, in the same way that like the root is the opposite or inverse of the exponent. Like you have x cubed, and then the opposite of that would you could look at would be this. That's what these are. Okay, and so this right here is everything. And again, I'm not including addition, subtraction, multiplication, division between these terms, because when it comes to identifying the category of an equation or an expression, you're not thinking about if it's being added, subtracted. You're just looking at the terms that are there, the types of terms. Okay, so it's not nearly as complicated as it seems. All right, so what we saw was that a polynomial expression was that if you looked at every single variable, okay, and then you might say, oh, well, it gets more complicated when you've got multiple variables. No, not at all. Like when you've got more than one type of variable in an expression. No, not at all. We saw that a polynomial expression was that you look at all of the terms in all of the variables, even if they're different variables. And if they're all raised to some whole number exponent, then you call that a polynomial expression. That's it. And you can think about when we talk about how to categorize an equation, it's going to be the same thing, except instead of an expression, it's going to be an equation. That's it. That's what a polynomial was. So now a rational expression is going to be the exact same idea as the polynomial expression, except if just one of the terms you have something like this, then you're going to call it rational. And you can imagine if it's going to extend past that. If you have just one of the terms as something like this, then you're going to call that a radical expression. If you have at least one of the terms that has something like this, you're going to call that an exponential. If it has something like this, you're going to call that a logarithmic expression. Now, you might say, well, what if we've got some mixture of all of these? Well, we'll talk about that in more detail later, but the way you want to look at that is it's kind of like going from here to here. Going down, the term further down, this arrow here is going to take precedence as far as how you're going to label the expression. So if you have just one of the terms has a negative integer exponent, or you could look at it like so here, right, we can't, this x over x squared minus 49, well, we can't really write this x to the x squared as an x to the minus 2 here, because it's like jumbled in with this x squared minus 49, but you have an x in the denominator of a fraction that's raised to a whole number power. Then that's rational, right? So if you just have just one term that has an x raised to a whole number power in a denominator, but you don't have anything else down here, but maybe you've got polynomial terms, then you'll call that rational. Okay. Now, if you've got just one term that's raised to a rational exponent, okay, but you have nothing, you don't have any exponential or logarithm, but maybe you do have rational terms or polynomial terms, then you'll call that a radical expression. Okay. Now, if you've got just one term that has an exponential like this, but you don't have a logarithm, but maybe you've got a radical, et cetera, then you'll call that exponential. Again, this is just a general rule you can use. Like, yeah, I mean, if you've got a radical and an exponential, then it's kind of got both like radical and exponential character in it you could think about, but this is a general rule you can follow that will work well. Okay, if you have an exponential, some number to the power x, one term, then you call it an exponential expression, even if you happen to have a radical or a rational term or a polynomial term. And then same idea with logarithm. If you've got one logarithmic expression, then you'd call that logarithmic. That's the idea, okay? So, but, again, the idea of a rational expression is you're focusing on terms with negative integer exponents. If you've got just one term so like if you had, this 4 over 5 x squared y here. Well, we know we can write this as, right, any negative integer exponent, then you call that a rational expression. But it's that rule there is a little bit, it's not all encompassing, because again, you couldn't, this x minus 3 over x plus 2, I can't write it with an x to the minus 1, but still, there's still clearly a variable in a denominator of a fraction that is raised to a whole number power. And so that's what you'd consider rational, just one. Like, it's okay, like you might have some polynomial terms. You might have, 5x squared y minus 2z plus 1 over k. Well, this is a rational expression. Now, if you just focus in on this one, that's a polynomial term. That's a polynomial term, but this is a rational expression in with three variables, or no, four variables. Okay. Now, from a technical math perspective, it says that what a rational expression is a ratio of two polynomials. That's the technical math definition of a rational expression, and that is true. I mean, like, 4 over 5x squared y, or any of these here, is a ratio of polynomials. But you might say, well, wait, 4 is a polynomial? Yes, 4 is a polynomial of degree 0 with leading coefficient 4. 1 is a polynomial of degree 0 with leading coefficient 1. It's a monomial. Okay, but the only issue that, like, this channel is more designed for non-math majors, and what makes that definition, what can make that confusing is that, any polynomial expression is a rational expression as well, technically. So, x squared divided by 1, right? These are all ratios of polynomials, but as far as the way I would suggest you to look at it as a non-math major is, I mean, if you want to remember that this is by the technical math precision definitions, that this is a rational expression as well, that's fine. But really, rational expression is you're going to have a variable in a denominator that's raised to a whole number power. Okay. So now, what you can think about though with rational expressions is that, similar to how with radicals, there were certain situations where you couldn't have certain values of x because you couldn't have a negative under an even root radical, right? You couldn't, if you had, well, here, y can't be negative. Okay, now, but we do know that when we fully understand complex numbers, that's going to take away all restrictions related to any radical. There's going to be no restrictions no matter, once you fully learn complex numbers. With rational expressions, there's restrictions as well because you can't divide by 0, right? So in this case, for this expression, x can't be minus 2, but different from radicals, even once we learn complex numbers, it's not going to change anything. Like, at this point in the year 2025, there's no scenario that allows you to divide by 0 no matter what kind of numbers you learn. So x is going to be, no matter what, 100%, x can't be equal to minus 2 in this expression. But again, if you're dealing with like, a lot of times we're just considering all real numbers, only real numbers. A lot of times in this before we really learn complex numbers, we look at problems, equations, etc., and we're considering just the variables are just real numbers. The solutions are just real solutions, etc. Then, in this case, no, x in this case can't be negative because you can't have a negative under an even index radical. Okay, so now what would the restrictions be in this case for this radical expression or a rational expression? What x's can't you input? Like, you can't. You have to look at it like we might simplify this. We're gonna learn how to simplify rational expressions in a second. But no matter how we simplify it, no matter what happens, you can't. You can start by looking. You can just, before you even start, you're going to say, okay, well, what can't I input here? Right? Like, and then once you've simplified it, when you get to the end and you simplified it, you're going to still, like, put, like, here, we can't put, let's see, we can factor this, x plus 7, x minus 7. Okay, so we can see x can't be 7, x can't be minus 7. So once we simplify this, then, and we get something else, we're still going to have to say, even in that simplified form, x can't be 7, x can't be minus 7. It doesn't matter what the simplified form is. Like, what if up here we had an x plus 7? let's just say that's what we started with. All right, well, these cancel out and we get 1 over x minus 7. Okay, that's fully simplified. Okay, so, all right, x can't be 7, but x can be minus 7. No. The original restriction was x can't be 7, x can't be minus 7, and it's still the case even here. Because all we did was we just simplified this. And it just condensed it down into an easier form to work with. But we're still talking about this, right? You see? Okay. So, but okay, let's talk about simplifying rational expressions. All of the different scenarios that come into play with simplifying rational expressions. Like we talked about this with polynomials. You combine like terms, and if you're going to multiply them, you distribute. So yeah, let's talk about how you simplify rational expressions, multiply them, divide them, etc. So, okay. A rational expression is simplified if, in lowest terms, if the only factors shared by the numerator and denominator are 1 or minus 1. Okay, so that's how you can look at it. Okay, with a rational expression, it's a ratio of polynomials, right? Well, we know how to factor polynomials, and so you can think about a rational expression as fully simplified it's kind of like if you factored the numerator and denominator and canceled out all of the common factors, then it's simplified. Okay, so to simplify a rational expression, factor the numerator and denominator, then apply the property of equivalent algebraic fractions. Okay, so equivalent algebraic fractions. Yeah, that's just saying how you can cancel common factors in the numerator and denominator. If you have AC over BC, well, then you can do this. That's what it's saying. Okay? And like it's the same idea when you have 10x divided by 15x. We typically just, cancel the x. 10 divided by 5 is 2. 15 divided by 5 is 3. But really more technically what we're doing when we do that is it's like you've got 2 times 5 times x, and then 3 times 5 times x. And you see we're canceling is what we're doing. Okay. So now let's see. This x squared minus 16 over x squared minus x minus 12. This is a rational expression, right? Yeah, ratio of polynomials, but just really we've got these whole number exponent variable terms in the denominator. So if you want to fully simplify a rational expression, you want to, since it's going to be polynomials, even if you had 2xy over 3y squared, that's a ratio of polynomials. But since they're monomials, it's like they're already naturally factored. A monomial is like naturally factored, so you can just go from there, and you'll get 2x over 3y. Okay, but here though, like these aren't. We have a binomial and a trinomial, so to fully simplify, you want to factor the numerator and denominator and then cancel the common factors. So x squared minus 16, that's a difference of 2 squares. So x plus 4, x minus 4. And then let's see, down here we'll get x 4, 3, minus 4, plus 3. Okay, the x minus 4s cancel, and you're left with x plus 4 over x plus 3, but you aren't allowed to, you can't input here, x can't be 4 and x can't be minus 3. Like, this is simplified, but you're still not allowed to, you can't input here 4. Oh, yeah, you can. 4 plus 4 is 8. 4 plus 3 is 7. No, but you have to remember where this came from, right? This is just a simplified form of this. You have to think about it like if you were to make some algebraic model and you modeled something up, right? and you got an expression like this. And okay, there's your model. You got it. It models something in real life. And then you say, okay, well, let me go ahead and simplify this down to something that's easier to, I can see a simplified form of it. And you simplify and you get this. Okay, so now what you're going to do is you're going to go ahead and just input all the inputs into this instead. Well, yeah, but the model is still this though. In reality, like you're still you just simplified it. You haven't the model is still this. So no, you can't. You're not allowed to input. Based on the model, it says no. You can't input a 4. You see? Okay, let's see. Okay, yeah, here's a good example. Well, wait a minute. No, this isn't a rational expression. We've got a radical. What's this about? No, this is rational. This is not a root of a variable. This is just a number. Like, right? Like x, this is x to the 0. This is just a constant. So yes, this is rational. This is a 0th order polynomial in the numerator and the denominator, with leading coefficient 8 plus 2 root 7 in the numerator and leading coefficient 4 in the denominator. So, okay, I mean, you could argue that this is simplified if you could argue that, but let's do this. Factored out a 2 here and got 4 plus root 7. Okay, and then 4 plus root 7 over 2. Okay, now in example 2a, the expression, the original expression and the simplified form are equal for all values of x for which both expressions are defined. Exactly. Yeah, it's really, you have to look at the original problem. So yes, no, you're not allowed to input minus 4 into the simplified expression. Or what was it? 4. You're not allowed to input 4 into the simplified expression, even though it works in that expression. The property of equivalent algebraic fractions tells us that we can divide out common factors that form a ratio of 1. We can also divide out factors that form a ratio of minus 1. Yeah, so when you notice that when you've got something like this, it's important to be able to see that you might look at this and say, oh, well, we can't do anything with this. But no, this is, you can take out a minus here and you're going to get x minus 4. Okay, well, there we go, minus 1. So yeah, you want to recognize when you've got these factors that they're only differing by, like, you just got to take out a minus 1, you'll get the same factor. Okay, let's do this 14 minus 2x over x squared minus 7x. 14 minus 2x over x squared minus 7x. Let's simplify this. So we can, let's just factor the numerator and denominator to see if we can get some common factors. So we've got a 2, we could take out 7 minus x. Then we've got an x we can take out, and then x minus 7. But you see, there's that, we can take out a minus here, and we're going to get x minus 7. Okay, now, there we go. But remember, minus 2 over x, but x can't be 0 and x can't be 7. Okay, so now that's simplifying rational expressions. Now let's talk about, with polynomials, we learn how to learn how to simplify them, combining like terms. We talked about multiplying them, etc. So now let's talk about multiplying and dividing rational expressions. To multiply and divide rational expressions, use the following properties. So, yeah, multiplying and dividing is going to be easy. You just, this is really straightforward. It's going to be a over b, right? There's a rational expression. C over d, well, we know what this is equal to. A, C over B, D. You just multiply the numerator and denominators and bring it together. So then from there, you're just multiplying polynomials. And then dividing is going to be easy as well. You do C divided by D, but we know how to do that. That's just, you take the reciprocal and turn this into you take the reciprocal of the divisor and then change the division to a multiplication. Okay. Now it says, but you to multiply or divide rational expressions, factor the numerator and denominator of each fraction completely, then apply the multiplication and division properties for algebraic fractions. Yeah, I mean, we'll see how to do this. You can, yeah, if you factor them before you like combine them, then you can just combine all the factors into one equation, into one expression, and then just start canceling them out. It's pretty straightforward. Multiplication and division of rational expressions is pretty straightforward. Okay, restriction agreement. Operations of rational expressions are valid for all values of the variable for which the rational expressions are defined. In examples 4 to 10 and in the exercises, we will perform operations on rational expressions without explicitly stating the restrictions. Instead, the restrictions of the variables will be implied. Yeah, so what they're talking about here is if we want to do this multiplication here, what they're talking about is that it's like we started off, we're given this expression. It's like we came up with some algebraic model for something in real life, and we got this. Well, no matter how we simplify this, it's like we have to remember that you start with here's your completed model. Well, okay, we can see y can't be 0, or else you're dividing by 0. X can't be 0, you're dividing by 0. Let's see, what else? X can't be, this would be, let's see, 3, or no, minus 3, or else you're going to get minus 12 plus 12. It's important to remember that. So they're going to stop stating the restrictions as we go into these further problems, but that's the idea. It's like if this was your model, okay, this is your completed model, like this represented some phenomena, this represented another phenomena, this represented another phenomena, etc. And you're done. Well, all we're doing when we simplify it is just cleaning it up. We're just cleaning it up. But we still haven't, just because we've simplified, we still haven't gotten away from the nature of the model itself. We're just cleaning it up. But the model itself says, look, okay, there's the model, but X can't be 0, Y can't be 0, X can't be minus 3, or else you're dividing by 0. So I don't care how you clean it up. Those restrictions still apply. And actually in this case, it's going to be really weird because, okay, so I mean, we'll work a bunch of examples. You'll get a sense for how to simplify this. What they do is they factor this, get x plus 3 squared. They factor this, then they take out an x and a y here. They start canceling out, and it simplifies to 1/2 of constant, which is really weird, okay? Because it's like what they're saying is that it doesn't matter. Like, so here we'd be inputting some, like an XY pair, right? You have an X and a Y, you input it and you simplify. But no matter what XY pair you input here, it's going to come out to 1/2, okay? But you have to think about this like it would be like if you had a computer program. You came up with a model, and now you've got some ATM machine or something that you're programming, and people can put inputs in. Well, in this case, no matter what input they put in, it's going to give 1/2. However, you still have to program into the machine that if someone inputs a point where x is 0 and there's any y, or y is 0 and there's any x, or where x is -3 and there's any y. If they input any of these pairs, then it says error. It says no, not a valid input. And then, but you'll say that, okay, but any other input that they put in, it's just going to just return 1/2. That's really weird to think about, but that's the idea. Okay, here's another example, and they're dividing two rational expressions. So they just take the reciprocal of this, and then we'll work a bunch of examples in the upcoming, the next video or the video after, where it's just you're just going to factor the polynomials and then start canceling factors. Okay, so that is multiplying and dividing rational expressions. What about adding and subtracting them? Well, this is going to be, so we need to make a common denominator. That's how we're going to do this. So here A, B, C, and D are real valued expressions, so these can be, A, B, C, and D, they're expressions. They could be any kind of variable expression. And so we know that if we're trying to add, if we if we've got a common denominator, then we can combine fractions. Then since we have a common denominator, we can do this. But if we've got a divided by b plus c divided by d, just as this sits, we can't do anything with this. And then, yeah, it says same idea if you had a minus c, and yeah, and then this is just, but like, yeah, b can't be 0. Okay, so, yeah, but if two rational expressions have different denominators, then it is necessary to convert the expressions to equivalent expressions with the same denominator. We can do this by applying the property of equivalent fractions. Yeah, so they're saying the equivalent expressions, meaning, so if you had a divided by b minus c divided by d, we can make an equivalent expression by multiplying by, if we multiply a over b by 1, then we haven't, it's still just a over b, right? So we can multiply this by d over d. And if we multiply c over d by 1, it's still just c over d. So we can multiply this by b1 in the form of b over b. So we have an equivalent expression. It's the same exact expression. We just multiplied both of the terms by 1, which doesn't change anything. And so what we get is we get AD over BD minus, and then BC over BD. Now we've got a common denominator, but an equivalent expression, but a common denominator. So, and there we go. Now we'll have, with the rational expressions, we'll have these polynomials, right? A times D is going to be a polynomial. B times C is going to be a polynomial. We know how to subtract polynomials, and but when we subtract them, we're going to get one polynomial divided by another polynomial. So we've got this new rational expression. Now we successfully subtracted or added the rational expressions. Okay, so that's the idea. Okay, so let's see. Let's do 7 divided by 4a plus 11 divided by 10a squared. Okay, so yeah, we can see these are rational expressions here. So we want to create a common denominator without changing the expression. So let's multiply by, let's see, the common denominator here is going to be, we need 20a squared is the least common denominator. So we need to multiply this by 5a over 5a and multiply this by 2 over 2. Right? And so we're going to get 35a over 20a squared plus 22 over 20a squared. And there's that common denominator. So we've got 22 plus 35a over 20a squared. And there we go. There's this new rational expression. We added two rational expressions and got a new rational expression. Okay, let's see. We've got 3x plus 5 over x squared plus 4x plus 3. And we're subtracting x squared plus 2x minus 3 and then x minus 5. So to see the common denominator, it's going to be easier to factor as much as possible. So, okay, here we're going to have x, and then we can do 3, 1, plus, plus, okay. And then here we can do, let's see, x, 3, 1, and then plus, minus. Okay, so we can see the common denominator is going to be x plus 3 times x plus 1 times x minus 1. So let's multiply this by x minus 1 over x minus 1, and this by x plus 1 over x plus 1. And so we're going to get 3x plus 5 times x minus 1 over x plus 3 times x plus 1 times x minus 1, and then minus x plus 3 times x plus 1 times x minus 1. And up here, we're going to have x minus 5 times x plus 1. Okay, and so then now we can combine these. So 3x plus 5, x minus 1, and then minus x minus 5 times x plus 1, and then x plus 3, x plus 1 times x minus 1. And then from there, let's see, we can factor out no, we can't factor anything out. Yeah, I mean, that's it. So now, I guess if you wanted to expand the numerator and denominator back out, yeah, that's what you could do, because you started off with these just two expanded out polynomials or rational expressions with the numerators and denominators expanded out. So if you wanted to, what you would do is just go ahead and expand all of this out. And so the idea would be, let's see, what would well, okay, I mean, let's go ahead and do it. I think this would be pretty interesting. So, okay, we've got 3x squared minus 3x plus 5x minus 5, and then minus all of this. So x squared plus x minus 5x minus 5. So let's do, okay, so 3x squared, then plus 2x minus 5 minus x squared minus 4x minus 5. So 3x squared plus 2x minus 5 minus x squared plus 4x plus 5. So 3x squared minus x squared is 2x squared. 2x plus 4x is 6x, minus 5 plus 5 is 0. So 2x squared plus 6x in the numerator. Okay, so we've got in the numerator 2x squared plus 6x. Okay, x plus 1 times x minus 1 we know is going to be, that's you multiplying conjugates there, so x squared minus 1. A squared minus b squared. So then we've got x cubed minus x plus 3x squared minus 3. Okay, so x cubed plus 3x squared minus x minus 3. So we've got x cubed plus 3x squared minus x minus 3. Okay, now, but can we simplify this anymore? All right. Well, okay. Let's the numerator. Let's factor the numerator. So we can take out a 2x, and we're left with x plus 3. Okay. Yeah. So if we put the denominator back into the factored form, x plus 3, x squared minus 1. Okay. So we've got 2x over x squared minus 1. There we go. So, that took a little bit of work, but it's interesting now that we can, our final answer here is, we were doing this subtraction here, and the result is, you see, now, but you would still need to, the whatever inputs, like the idea is, another way of looking at this is, so you would figure out what values you can't input into these, right? Would you be dividing by 0? And so let's see, what would that be? X can't be minus 3, and X can't be 1. And that still applies here, because another way you could look at this is, if X was minus 3 or X was 1, then you couldn't have done this subtraction to begin with. The subtraction wouldn't have even existed in the first place if X was minus 3 or X was 1. So how could you put that in here? See? Okay, in the next video, we'll talk about complex fractions.